Now, okay, so welcome to the 5th edition of the EMEA Online Meetup. Today, as a main presentation, we're talking about fairness of predictive models. Wait a second, I will mute everyone, and if you wanna say something, then just unmute yourself. Oh, where can I do this here? Okay. So yeah, today we're talking about fairness of predictive models. Very interesting topic, I think. And Krishna, who is already on the line, is going to present it. Krishna is from San Francisco, right? Yeah. Okay. US people presenting on the EMEA meetup. That's very good. For people from the US, it's pretty convenient, the time. When we from Europe want to participate in the US meetups, we have to go for like 2 a.m. or something. Yeah. Okay, so first a little intro, and then we will have about 10 minutes for community discussion where we can discuss recent stuff you want to talk about. And then we have 45 minutes combined for the main presentation and question and answers. Krishna, if that's okay for you, I would say that people can ask questions during the presentation. Please keep in mind that you don't stop Krishna every 10 seconds. So if you have a very important question during the presentation, then you can ask it. And maybe after the presentation, we can talk about some more detailed questions. Yeah, okay, so I already announced this last time, but next time we'll really do the hands-on tech special, Docker for data science. And yeah, that's for March on the EMEA meetup. And the US meetup, the next one is about implicit self-regularization in deep neural networks. Also very interesting topic, taking place on February 20th. And if you want to participate in the meetups, I guess most of you will already get the notification emails. If not, head over to twimlai.com/meetup and register. You can always change your preferences for the notifications, yeah, so that you can get up to speed with what's going on TWiML AI. If you want to present a paper yourself, please reach out to me at Kai on Slack, or Kai Lichtenberg on LinkedIn or via email. Also, if you want to propose a tech special, so we did one tech special the meetup before the last meetup, which I think was a very good thing. And if you have an idea for a tech special or want to present something, please reach out to me. That's also very interesting. So I think we'll do like 2 paper presentations and one, so 2/3 paper presentation and 1/3 tech specialist. I think that's maybe a good thing to do. Also, a new Fast AI study group has formed. I think on Saturday was the first meeting of this study group. Is anyone on the line who is participating or even hosting the study group?
Yeah, I'm part of the host as well as I'm attending.
Awesome. So you, that's correct what I said. You just started last Saturday, right?
Yeah, that's correct. That's correct. We did lesson 1 plus a couple of presentation, and that's going to the format lesson 2 onwards.
Awesome.
Around half an hour, 40 minutes, discuss the lessons, and then rest of the time, 2 presentations.
Okay, awesome. So, and the plan is to do the part 1 course, and it happens to end when the part V3 part 2 course is starting, right?
That's correct.
Okay, awesome. So if you wanna join and do the Fast AI course, that's about the best time to do it. You can also subscribe on twimlai.com/meetup, and you will get the notifications for the meetings. It's at least in Europe, it's I think 6 p.m. and in the US,
it's the 5 p.m. GMT on a Saturdays, and I think it's 9 a.m. EST. Oh,
Yeah, okay.
I'm not.
Just
I'm
look it up or ask
available.
on the Slack channel. You will, someone will tell you at which time this takes place.
Yeah.
Yeah, as I just said, just unmute yourself and ask a question during the presentation if you want to ask something. Also, you can submit questions via the Zoom chat. I will try to open the chat and forward questions to Krishna. Okay, so that's about the intro. Now, if you want to discuss anything about recent shows or upcoming or ongoing courses or any topic you want to talk about in machine learning, then just unmute yourself, jump in. I will wait a few seconds if someone has to say something.
On Saturday, I'm going to present a paper in the US FastAI study group called Learning Independent Causal Mechanisms. If someone is interested in that, I think the European time is 1800 military time, and I'm not sure what the US time is. You have to look that up.
So it's the FastAI course we just talked
Yes.
about. Yeah, okay, awesome.
Yes.
Interesting. Okay, so I have a few things that I stumbled upon in the last weeks. So this, for example, that's something I really found very interesting. Maybe some of you know that. It's a pretty popular GitHub repository, which is collecting papers that where also code is provided. So they are basically watching all the important conferences, and they save all the papers that are providing code. So when you click, for example, here on this video synthesis paper and click on code, you will get forward to the code repository. So it's a really, really big resource of, I mean, look at this. This is only 2018 here, I think, everything. It's really a lot. So you probably can get a lot of, this is, okay, so this is 2016 and this is 17 and 18. So there's really a lot of code in there. It's a really good collection. So I will post the link on Slack in the meetup group. Interested in that, go ahead and look at it. Yeah, so that was one thing. And then also I found one very interesting thing someone did with the FastAI library. Probably a lot of you will have seen that. Jeremy Howard tweeted about that. And it's this DeOldify using GAN networks to colorize and DeOldify old image. And I found that really, really interesting. And I mean, look at the results. That's awesome. And also, they're not telling the network how they should colorize the images. And it's very interesting how, I mean, it really looks interesting and really realistic, right? So
I think it looks interesting. Yeah, I'm actually impressed like you.
Yeah, I mean, it's pretty accurate in terms of color. I mean, look at this, all the features from the person. I mean, okay, so the hands have the same like the shirt, I think, but there are some very small things. It's really, really very interesting application of general adversarial networks. The code is also in this repository. I will also post the link for this in the meetup group. Okay. Some more, did someone hear about this conversation from LeCun with, I think, Ali Rahimi about machine learning becoming alchemy? And so that there's some missing rigor and it's too much driven by getting practical results on machine learning. Does anyone a take on this?
I haven't read it, but I think it's
last year, right?
a very interesting subject.
Yeah.
Yeah, that was the Test of Time acceptance speech 2017 at NewEps.
Yeah.
It's worth watching. Like, whatever your take on it, it's definitely worth watching.
Yeah.
Another speech.
Yeah, I kind of felt reminded on. I mean, I'm by training I'm a mechanical engineer, and I always thought about that. So much in engineering is based on kind of it's on empirical stuff. So all the everything you're driving, your car or any kind of structure you see, it's all based on kind of empirical material science stuff. And this is so in engineering disciplines like mechanical engineering, or sometimes also in electrical engineering, it's very common to do this. And I kind of felt this is a little. So I'm more on the engineering side of really getting practical results on that. But I can also understand that in science you wanna have more rigor methods to evaluate performance.
Yeah, I agree. I mean, empirical results are important, but I would say that I think Ali's real point is that often these results are not reproducible, in which case they're garbage. So we need rigor. Both theoretical rigor is good to have, but really we need rigor and reproducibility. So that papers with code repo is new to me, and that looks really
absolutely. Yes, absolutely. And also next time in March when we talk about Docker and data science, that's also one very good method to have reproducibility.
Plus, Kai, I think, mechanical engineering, after all, I agree that a lot of stuff is like hacking and so on and like tweaking stuff, but there's certainly physical theories behind everything you do. Yeah,
but not so much not so much. I mean, everything that I did in for example, calculating the strengths of gearboxes or the fatigue strengths of gearboxes, for example, it's completely based on some statistics and on empirical results from material stress probes. So of course there's some physics involved in that for sure, but it's not so much. So people think it's more based on really science and physics than it's actually, I think.
Okay.
Okay, so I think we can now go for the main presentation. Krishna, if you want to grab the screen.
Oh, yeah. It's kind of interesting that blog post. So it seems like you have to stop the screen.
Okay, yeah. Stop sharing. Okay.
Okay, can people see it?
Yes.
Cool. Yeah, so just a couple of minutes intro. We are a small team in California working on this explainable AI engine. In fact, like Jan LeCun's post and Ali's talk are very relevant to what we are working on. We're working on tools and platforms to make models interpretable for data scientists. So I was until recently I was at Facebook working on sort of machine learning interpretability for newsfeed, and before that I was at Pinterest, Twitter, and Microsoft. And yes, is Luke, is our data scientist. So today we're going to talk about this paper. This paper was nominated as the best poster paper for NeurIPS last year, and very interesting paper. Talks about, I think there's a lot of theory in the paper. So what we're going to do is we're going to talk about it at a high level, and then there's actually these two posters and the slide deck from the same presenter that actually are more suitable for a presentation point of view. So we can sort of basically walk through those slides. So the main point of it is essentially, as people know, like when machine learning algorithms have this issue where you have like, let's say you're doing some sort of healthcare diagnosis or job application prediction, and you have multiple demographics in your data set, you might find that the predictions are unfair to a certain demographic or unfair to a certain group, right? And so like how do we actually solve this problem? That's basically the main topic around fairness. And so people so far, and the paper cites about the approaches that people have taken in the past, where you actually sacrifice your accuracy in favor of fairness. So you actually try to make like the model underperform for for certain groups to actually make it like more uniformly performant across the groups, right? So the paper talks about like how this, in fact, applying these kind of techniques where you actually make the model underperform would actually be pretty detrimental in cases where, like, especially if it's like someone's health or someone's like life on the line, right? If it's being used for criminal justice or healthcare and those kind of situations. So it talks about providing a framework of how do you actually define fairness, and within that framework, given each situation, what are the things that you can do, right? So essentially it defines this fairness metric as essentially a composition. So for example, if you go to this is basically, so it talks about like fairness as, if you think about like the main prediction and the optimal prediction, what's the difference, what's the error between the main prediction that your model is providing and the optimal prediction, whatever like the God-given model that would be, and so it composes that error into this combination of a bias, variance, and error, and sort of like the noise, right? So essentially, so an error in this case, it defines gamma A. So error for a given, for in this case, it's A is a protected attribute. So let's say you have some sort of like a college applicant prediction model, and your attribute is race. So you maybe looking at like, okay, so what's like the error for the protected attribute race, and so you can actually decompose the error into like a combination of bias, variance, and noise. And so the paper talks about like actually proving this thing. And so that the question is like now, so now how do you actually define discrimination, right? So the discrimination is like the difference between like the bias of like, let's say an attribute being, let's say it's like male versus female. So like male is class 1 and female is class 0. So it basically talks about it essentially as the difference between, essentially is the difference is the sum of differences, an absolute sum of differences in bias, variance, and noise, right? So that's basically what is defined as, this is the expected discrimination. And so now this provides a model in where you can actually see in what situations you have discrimination due to bias, in what situations where you have discrimination due to variance, in what situations you have discrimination due to noise. And each of these situations, what are the approaches that as a practitioner you can take, right? So essentially you can have a situation where you can have a model that has a high bias, right? So essentially maybe it is not for a certain group, let's say the female group, the model is highly biased, and so the paper suggests basically like you have to sort of like change the model class. So for example, I think the slides here are pretty good actually.
So just so that I understand that, you, for example, when you have a feature like male and female in your data and want to predict something, then you have a look at the differences between the predictions for male and female, and then you kind of assess what there should be no difference, as your ethics say there should be no difference for this particular case, and then you can measure the difference between them.
No, so I think like usually the way you have to define this is you should say there should be no difference in false positive rates or false negative rates or whatnot, and you actually might make your model underperform for male, right? Like, so so the paper argues that that's not the right approach. So let's actually define what fairness is, and it decomposes this unfairness into these 3 components of like bias, variance, and noise. And so then each situation where if it's like a discrimination because of high bias or a discrimination because of high variance or discrimination of high noise, it proposes 3 different approaches that we can take, right?
Okay.
So if like discrimination due to high bias, then it proposes you need to actually try like a better model for that group, right? For that category of people. If it's a discrimination due to high variance, then it argues that you actually have to collect more sample data for that sort of group. And if it's discrimination due to high noise, then you have to collect more features. So that's basically the gist of it, right? And so we can sort of go through the slides and it becomes clearer. So that's basically, in this paper, it talks about the source of fairness and how do we sort of like decompose it and demonstrate methods to either you do feature augmentation or you actually improve training data collection to actually fix the unfairness. And so,
so one thing. So when you wanna, in this framework, want to define, so bias can be different for different use cases. So when you wanna, I don't know, see if someone's is good for a job you wanna give someone, then bias would be bad towards a male, for example. And but when you look at, I don't know, sports maybe, where there is a difference and you maybe want to have a model that can show this difference, then you have to define a different context, right? So
yeah, so so the paper here defines, like, so first of all comes up with what is a fairness metric, right? So how do you define the fairness of it? So it defines fairness as the absolute difference between your, like, so your sort of like prediction, which is like, let's say y hat, and the sort of the difference between like the predictions between the predicted attribute and the like sort of, let's say, men versus women class, right? So for example, so right now, so for example, if you look at it, so gamma A is essentially the error that is a discrimination for this protected attribute, or for this protected attribute, in this case like gender, is essentially defined as bias for that protected attribute for that prediction model y hat, and some of these, like the error in variance and some error in noise, right? And so let's see.
Yeah, Kai, I would also chime in. So the term bias is very hard because there's a statistical meaning, and so this B actually doesn't refer to unfairness.
Yeah, it's the statistical meaning of the bias.
So
sure, yeah.
Here we'll use the term fairness or discrimination. So this large gamma is actually the measure of discrimination. That is actually this. Yeah. So this capital gamma here. This is the discrimination level.
Yeah.
So this is what we're worried about. If this is not 0, then we have unfairness.
Okay. Sure. Yeah.
These terms are actually just a measure of how like a linear model can't fit to a curve.
Yeah.
That's bias.
Yeah.
So,
got it. Yeah.
Statistical bias and fairness, discrimination are two different concepts, and the terminology is just difficult.
Yeah, so, absolutely. Yeah, sure.
Yeah, so for all it's worth, we are basically talking about like this, we're computing this discrimination, expected discrimination level, or this number that tells us if this algorithm is fair or unfair. And so going back to sort of like the examples, let's see. So as I said, we come up with this, what is this, like, what does this fairness mean? Like, we can come up with this sort of composition that this fairness is this composition of bias variance, the statistical bias variance and noise. And wait, why did it? Weird. And here are some references here. So then it talks about like we should examine fairness algorithms in the context of both data and model. So far, like the argument is like only people have addressed it from the model accuracy perspective, where you actually reduce the accuracy of the model or try to make it even across the groups, and then sort of like call it like unbiased. And so in this case, it actually gives us a better framework. So now let's ask about why might your classifier be unfair, right? So now let's say if these are the two data points. Let's say the blue are male and orange are female, right? And this could be some sort of like applicants to a college or whatever, like your data set is. And so maybe there are two generating data functions. Maybe like orange data function generates like the orange data points, and the blue data function generates the blue data points. And you can fit a model, right? So maybe you can try to fit a model that actually sort of is trained on these data points, but you can actually see like whatever model that you try to fit, it will have higher variance for the orange data points. And the reason is because there's so few, you just basically cannot avoid it. So what for cases where you have higher variance, higher statistical variance for your learned model on a particular category of data points defined by a particular attribute. So the framework suggests that you have to collect more samples. Like in order to make that more fair, you have to sort of like collect more training data for that in this case, like the female data points. And another example is like, let's say this is the distribution of your data points, where orange now is like this has this quadratic curve, and so now you can try to fit a curve that fit a model that learns this from this data. And so again, here you can see that this any model that you can fit will not be able to fit very well for the orange, because it's a linear model trying to learn for the quadratic this thing. So it'll have a higher the orange dots will have a higher model error and compared to the blue dots, and because like the orange dot sort of generating underlying distribution is actually quadratic. So it talks about now in this case you have to train a separate model for the orange class, right? So in this case, like you may have to sort of choose maybe like more complex model, so that reduces the bias, the statistical bias.
Krishna, I already have a question. You've just shown, or the heading was why my classifier is unfair. Yeah. And then it looked to me like a linear regression. So it's not a classification problem, but a regression problem in this case.
Yeah, so this paper actually presents a proof for both classifiers and regression setting. These metrics are a lot more understandable. Like, one group has a higher false positive rate than another group, and you're, classifying recidivism in inmates. It's important that you have a fair false positive rate across classes. So the discussion is usually done in terms of classification, but then the actual theory applies to both classification and regression problems. And here for the visual example, it's more intuitive to look at the classic linear regression example. Classifiers don't have the same kind of 2D scatter plot feel. So yeah, that was a really good point you made. The general decomposition applies to both classification and regression settings. And the heading is just kind of from the paper name.
And in the first picture, it also could be a boundary, right? So.
Yeah. So it also, if we're talking about nonlinear decision boundaries with linear separation, some sort of hyperplane in like an SVM or a logistic regression, then we can get into that type of situation as well.
Yeah. So and so the third situation. So the third situation is where you actually have like the orange data points all over the place, and so like no matter what kind of a model that you train on the group, it won't be able to do very well with the orange data points, because the model error for orange data points will be pretty high for whatever model they choose compared to the blue data points. And so in this case, like there's a lot of noise within the data. So the discrimination is not coming from because of high statistical bias or high statistical variance. It's actually coming from the noise within the data set. So the argument is to actually collect more features and get sort of improve the features part of the data. So that's basically what it is. So essentially now it talks about like how does like the theory work behind it, right? So now so as I said, like it composes this sort of model error as this sum of like bias, variance, and noise, and so as a result, the discrimination is the difference between model errors for the two protected groups, in this case, two protected classes 1 and 0, and so now it basically, so in this case, they've run some experiments. They basically sort of like took some clinical data and tried to predict like the mortality rates based on the clinical data, and they found that like this, like for example, for like Asian and Hispanic groups, like they had like sort of higher sort of like higher error, and so they talk about sort of like how do you sort of do it. So for example, in cases like, I think this is where I think the paper gets, maybe we can actually go to the paper here. So let's see, well, maybe here. So here they basically talk about like, hey, so we predict, so the first, there are two experiments that they've done. One is the income prediction, the other one is the clinical mortality rate prediction. For the income prediction part, they basically took this census data set that actually had features including age, sex, education, marital status, and they trained this random forest classifier. And so they found that the accuracy for women actually differs by men by whatever, like basically just 0.085, some confidence interval, right? And so they basically, they found that in this case, if you actually subsample the data, and if you actually just like try to increase the training set and sort of like extrapolate it, so the discrimination or the unfairness actually goes down, right? So your false positive rate and false negative rates actually for the two groups, so for both women and women actually meet at the same time. So this is something very interesting because this is basically what the sort of like the variance-based discrimination case, right? So where in this case they actually showed that by increasing the training set size, they were able to get similar sort of false positive rates and false negative rates for across both classes. And so this is basically where the remaining error, therefore unfairness, is noise and bias. So once they fix this thing, we can estimate that the infinite data limit, which corresponds to no variance, then whatever the remaining error is present is basically due to the noise and bias, right? And so in the second experiment, they basically take like this the clinical data which like uses the first 48 hours to predict the next sort of like 48 hours what happens like to the patient.
Can I ask one more question for the last thing? So what I basically understood is that by adding more data, they kind of say, and extrapolating this, they kind of say that they can get the error down so much that there is no more bias, right?
Yeah, there's no more bias. If there is any bias, that is only coming from, there's no more unfairness. That's, I think the word bias is like, there's the statistical bias and there's bias, the colloquial bias.
Yeah, sure. I mean the statistical.
There's no unfairness.
Because it's better generalizing, it's getting less statistical bias there.
Exactly.
And how can they rule out that this is not a model issue?
Yeah. So in this case, they basically, I think in this case, what they prove is like where if the discrimination, like in this case, the discrimination that they found, right, like between the two classes, was mainly coming from lack of training data, right? Like, so you can actually, like, if you just like add more training data, or you actually subsample and go and extrapolate the training data, you actually can actually show that whatever discrimination, whatever unfairness coming from variance can be solved by increasing training data. So whatever is remaining is actually is inherent, like is one of these two problems, right? Is either we may need a better model class for women, or there's probably noise in the data.
Okay, yeah, but it's not. It's something that they kind of estimate, right? It's not. They do not prove that they can bring down the bias to zero in this case.
Right. So I mean, they point out there's this kind of rich body of empirical evidence around these type 2 learning curves where if you plot training set size on the log axis and then like error rate, it goes down. So if you look at the error rate of each class, they both follow this curve. And so they show that like when you have 10 times as many male samples as female, your model just learns the patterns in the male ones with less overfitting because you have 10 times as much data. If you equalize your data set size, they can show, if they have 1 million samples, if they take 1 in every 10 male samples and every female sample, they can show that there's no bias.
Okay.
So
it's kind of an empirical thing that they know this curve is going down to zero basically, and it's not going to flat out on some point. And because what I just thought is that maybe the error, the curve could get flat, and then the rest is induced by the model, for example, because it's not capturing everything correctly.
Interesting thing is in the second example that doesn't hold true, right? So in the second example where they actually had these 5 classes of like races, and they could actually subsample the training data size and actually experiment at various training data set sizes, they actually don't see the error rates coming and converging, right? So this is a counter example where your unfairness is probably not coming through variance, and it's coming through other means. And so then they basically talk about like how do you if it's coming through noise, so how can you sort of like look into that? So then they look at basically techniques where you can cluster your data points and figure out like, okay, within each, what are the different clusters that like maybe there you don't have enough features for, maybe like you have cardiac patients and cancer patients, and so you need to sort of like add more topical features and whatnot to actually sort of improve the model, right? So this is a case where the unfairness here is actually not coming through lack of training data, but more so sort of noise in your data and actually lack of like good features, right? So so this is basically sort of the second example that they talk about. I guess here, yeah. So that's kind of what it is. So the main takeaway from the paper is when you actually have a machine learning algorithm, how do you measure the unfairness of the algorithm? This is like sort of one methodology. And when you have unfairness, how do you measure whether the unfairness is coming from the statistical bias of the model or the variance, statistical variance, or the noise in the data? And so for each of these situations, how do you fix that, right? So so that's basically the main takeaway.
Yeah, I mean, so I think now would be a great time to pause and see if people have questions or all that. There's also, I'm happy to go into kind of a hypothetical example to help kind of concretize some of these ideas of bias, variance, and noise as well. But let's definitely pause. Does anyone have any thoughts? Also, not just on the math part, but on kind of the implications for DBias and fairness in general.
So if I understood correctly, fairness is basically defined as having a homogeneous error profile across any subgroup, right? And group here, like we've been using group to mean like maybe male or female or whatever, maybe split into geographic regions, like with ethical considerations, but in fact it can just be any arbitrarily chosen subgroup, right?
Yes. Yeah. So yeah, in these problems, oftentimes there's an added complexity of that it's not like permitted by law to include these subgroup features in the model. Sure. So often there's this kind of that there is a nuance there, but yeah, exactly. You can choose any two subgroups and compute this discrimination metric. If you have discrimination between people who are in like on height or something that's not legally protected, that's usually not as much of a concern to practitioners, but this metric is applicable to anything.
But so what I'm thinking is that like ethical considerations aside, and they are obviously like clearly extremely important, and this is great. It's great that so much work is happening on this, but it's just a good diagnostic tool for when my model sucks, right?
Yeah, absolutely. So I think like as you can see here, right? In these plots you can see like your protected attribute could be whatever. Like so you can actually see if you is your sort of feature data very influenced by your protected attribute. In this case, like your features, like whatever, maybe university or something. So maybe these two are two different like races and they're two different universities or whatever. The feature could be the protected attribute could be whatever. And so you can actually see if your model is underperforming because of statistical bias, right? So in this case, like it's actually like underperforming well for like a particular set of like sort of demographic versus like the other demographic. In this case, they argue that you have to change the model for that demographic. And wherein your protected attribute is actually not influencing anything. In this case, they actually have the same sort of distribution. And so then it's a case of where your model is actually underperforming for that particular demographic group because there are not enough samples for it. So it's kind of like you go and increase the training set size. And yeah, so I think you can actually use it for any subgroups of any clusters to actually figure out like where your model is having the higher error and actually how do you fix it.
But I think it's a nice tip to say increase training data size, but I guess in practice, how would you do it? I mean, it's always better to have more data, but your data set is basically fixed. And do you buy then more additional sample size, or how would you do that? I mean, that is not always feasible in practice, I think.
And what you could do is kind of artificially reducing the data, and then look what happens if you add more data. That's something you can do if you have enough data for that, probably. And yeah, more data is not always feasible. Sure.
Right. I guess it depends what your objective is. If your like most important objective is to not be biased, then you subsample the dominant class. So,
right.
yeah.
Although this goes back into some of the techniques, de-biasing techniques, because you can always, a very, very simple algorithm to make things fair is that if you have one class that's better, your model is better on than the other, you just randomly add noise to your predictions or you flip them. So, but imagine the real world applications. I mean, like, people are using these types of models to predict whether a criminal is going to be a repeat offender when they're looking at parole. So if you just say, oh, our model's too good at predicting white men who are going to commit a crime, we're going to just randomly flip our prediction of whether you're going to commit a crime or not and give you parole or not based on a coin toss that we've just added to our model. Yeah, that may be fair to all of the other protected classes of inmates whom you don't have the same performance of the model. But is that truly fair? In terms of your discrimination level metric, yeah, you've achieved parity. But in terms of true like ethical fairness, this paper has pointed out that approach, that a lot of academics have just kind of clung to this metric and forgotten about the real world, that's completely unfair. You can't toss a coin and decide someone's fate.
Yeah, sure.
So, and in those types of applications, I mean, it is very, if it's that important, collecting more data is something that you can usually justify to the business decision makers. If you're in lending, you may actually just experimentally offer credit card lines to people who are unqualified by your current models to gain that data. Even if you end up losing money on those lines, that additional data has a greater value. There's actually case studies of that. Capital One actually is famous for doing that very thing.
Yeah, that's a particular expensive thing to do to get more data, but yes, yeah. Sure.
Do you know if there's any intersection of this with like the active learning community? So in principle, when you collect more data, you don't have to just collect more data randomly. You can like target data points that would have high entropy or like high uncertainty or something, so you can like have a more data efficient learner.
Yeah, this paper, I mean, was squarely within the supervised learning kind of batch learning framework. And so their technique, they use a clustering technique to identify subgroups for which in terms of collecting more features, where certain subgroups where there's not enough discernment between members of that subgroup. So if your model is not performing very well, it's kind of grouping all these people together. How can you discern between a very similar homogeneous subgroup? You have to collect another feature. So there are these diagnostic tools presented, which we are happy to go into some of these things that they talk about later in the paper. But I don't think that this paper in particular really did anything more than just mention in their conclusion section that they're related words.
So is there any like library, like a Python library or coding side of it, so that I can feed in my model and see
if it's fair or not? Yeah. No, I don't think there was any code that came with this thing, but I think it's not very hard to implement some of these techniques proposed here.
I mean, you can wrap it around the model, right? So.
Yeah, I mean, it is, there's some subtle points. So, like, obviously with the statistic, it is an absolute value of a difference. And so, like, you're always going to have some positive number due to just statistical variance. And so they present in the supplementary section statistical tests for significance of this bias to be able to determine if you actually have bias or if it's just statistical noise. And so, like, implementing that may not be the most, you'd have to read the follow-up section and completely grasp the statistical derivation. So, I think this is an area where it would be great if we actually had more open source solutions and more attention paid to this area. And I think that's largely what Fiddler is doing just in general with our mission to kind of create usable tools for explainability.
Well, feel free to talk a little bit about that. Don't be afraid to do some advertising for a young startup. So if you want to talk a little bit about that, no problem.
Yeah, sure. Yeah. So I think, basically what we are trying to provide is a sort of a toolkit for data scientists to be able to explain black box models, to get insights into like what features are actually contributing, what's the feature impact, like how does the model performance, like for example, this kind of clustering, right? Like you maybe have two models that you can actually find like where are the underperforming data segments that exist, right? And so like you can actually go and so you can actually cluster by whatever. In this case, they suggest clustering based on protected variable attributes. We can provide the toolkit to actually be able to cluster on whatever feature that you want to, and then figure out what data segments at each, like one model may underperform better because your aggregate metrics may not reflect that thing, and also sort of like be able to sort of do explanations over like at a point level, at an aggregate level, over a bunch of data sets, and then eventually also getting into more white box explainability, right? Sort of like how does it like when you actually run an input through a model, what are the different parts of the model, especially if it's like a complex model like a neural net or which neurons are getting activated and whatnot. So those are the tools that we are building for data scientists, and the idea is that people, when they build a model, they can use our tools to do design time debugging, right? So we think like if you kind of talk about like machine learning as this software 2.0, the critical sort of developer tool that is missing is a debugger that you can actually use on a regular basis to actually debug how your models are working and get more insights, and so that's kind of what we are working on, and so yeah, I mean, we are very excited about the paper, sort of like these kind of papers, like where we can actually provide these insights into the platform, and sort of like people can and sort of see, okay, is my model being fair, or like where are the opportunities for my model for me to improve my model, right? So that's kind of what we're looking on.
Are you adding in data sets as well to that? Are you adding in like, yeah.
The input is the model and the data set. So yeah, I mean, we are actively working on it. We once we have a product that is in a beta state, we are happy to share with this community. Like we want like more feedback. So yeah, the input from the data scientist is a model and a data set, and you get all the analytics in sort of visual, sort of cloud-based UI.
So in your data set, are you attempting to create an unbiased data set, or are you creating a collection of biased and unbiased so that you can have some discriminatory ability to determine whether your model, because it was trained on limited training data, which has inherent unfairness within it, I won't use the word bias, can you even characterize or is there an experimental or, pragmatic way that you can essentially determine whether your data set is too narrow?
Well, I mean, the data set is supplied by...
Sorry, go ahead.
So the data set is supplied by the user, and you can tell us which one of those, like your data set is essentially like a feature and value matrix, right? So you can suggest like these are the features that are protected, so and so. So if you want, so then our system can actually suggest you, like you can basically do something like this, right? And it can actually show you, hey, like this is what we characterize the unfairness of the model on this data set. And if you, along these protected attributes, right? So let's say you may say like they have these 3 protected attributes, gender, sort of race, and whatever, zip code or whatever. And so you can actually see the model performance across those protected attributes. And you can decide whether you need to add more samples for a certain attribute, or you have to undersample some things that you may be like sort of overly represented in the data set. That's up to the data scientist to figure out. We provide the insights.
Yeah, and I think your question also gets into the kind of the diagnostics presented in this paper. All 3 of these terms, like this decomposition works in mathematics in the expectation of some data generating process that is fixed but unknown. But the key word there is unknown to me. As a practitioner, like it's very difficult to actually approximate most of these terms. When you do stuff with data set subsampling, you can sort of, if you make assumptions about learning rate curves and fit a parametric representation, you can do things like kind of forecast. Okay, so how much, if I collected infinite amount of data, where would my error rates end up? And then what does that say about how much of my error rates are attributed to variance, which goes away as you collect infinite data, versus model bias, which doesn't change unless you change your model, versus noise, which is just inherent in the relationship between the actual variables in your input and the variables in your output. So you either need to change your entire task by adding input variables to get rid of noise, or change your model if you have a kind of indication there might be bias, or potentially you can collect more data, which is actually one of maybe the easiest outs, because oftentimes you spend a lot of time creating this really powerful model and tuning it, getting the best overall performance, and then you realize that there's one protected group subclass is biased by your model, because your model actually is not flexible enough to fit both, but you don't have enough data to use a more complex model, and you end up, it's a very complicating, challenging area. So, I think our focus is just really, we want to get these diagnostic tools and start just at least asking these questions, because sadly, there's just not really a one-size-fits-all answer. These learning curve extrapolations are very valuable. Subgroup clustering can be a very powerful diagnostic tool as well to find out exactly what might be causing disparate performance across protected subgroups, or even not protected subgroups. Like I think Chris earlier was mentioning is a Uber Manifold is a tool that was just recently kind of demoed in a blog post that they do a clustering on kind of subgroup their data points by performance to identify what is causing poor performance in the subgroup that actually has a bad error rate compared to the overall where your model might be doing well. So some of these questions being answered, it's fascinating overall. Yeah. This answer is a little meandering, but
so yeah. I think this is something that we used to see quite a bit at Facebook. So because Facebook in newsfeed, you have this heterogeneous collection of stories, right? And whenever a new product gets introduced, let's say a new type of story, let's say charity donation story, and it gets introduced into feed, it would get consistently lower predictions because the model doesn't have enough data. We don't know enough about those donation stories. We don't have enough training examples from people clicking on or liking those donation stories. So as a result, their predictions are pretty low. So the way we would address those problems is to actually sort of split out and kind of do this bias-based approach where you sort of actually carve out train a separate model on only for those stories, and then sort of try to merge those predictions within the overall sort of model, right? So I think this is something, bias in the world of fairness. This plays up, but even otherwise also you do have when your model performance. You may have a certain data points where your model is significantly underperforming and there's a lost opportunity to actually improve performance. And how do you detect that and how do you address that is still a continuous problem for many companies. And that's something.
Very good answer, thank you. I just have a much simpler question, I guess, which is, do you think, is your tooling, or do you think it will be possible for data scientists to have a kind of dashboard where they can essentially feel comfortable that they are doing a, not perfect, but a pretty good job of their model being fair, and only intervene when needed, when a bias or an undersampling has occurred, you essentially raise an alert and they can then respond to that? Or is this more of a kind of a support tool for a developer who's constantly looking at this and you're just providing mechanisms? I mean, how do you see this playing out?
Output is a dashboard. So the just kind of more practical point of view is you give the system a model, which is kind of some Python code that you need to write, and hopefully within a month or so we can actually demo this. And then your data set, which is whatever CSV file or whatever data set, whatever format that you may have it, and all the analytics are basically dashboards. So you can get the analytics around explainability, like what features are impacting your models, pairwise correlations across different features and predictions. You can get model performance split across different segments and different clusters, and some of those clusters can be defined by you around those protected attributes or whatnot, right? And so then, and as a result, from these charts, hopefully you'll be able to figure out, is the model actually underperforming on a subgroup or whatnot, and in this case, what you need to do, right? So we have not yet decided, should we actually propose implement an unfairness metric and say that this this model is unfair or not for various reasons. But we can actually provide you all the other tools that you can actually come up with your own sort of a way to determine if the model is being fair or unfair. So because we don't want to be in the place where we could call this model is fair or unfair. That's something that we want to leave to the practitioner.
And also what there's one thing that especially business people and all the deciders should keep in mind, and that is that this cannot help with bias that's in the data. So if you collect data that is already biased because, I don't know, it's collected by people that have these biases, so these non-statistical biases, and imprinted this into the data, that's something that cannot be detected by this kind of models. I mean, it's math, right?
Yeah, so actually, I mean, to give a couple concrete examples of this, you know, there's recent buzz around not Facebook, sorry, Amazon's recognition platform. The protected class of darker skinned females, there's a much higher error rate there. So if you look at this gamma function here, let me see if I can find where it's actually originally defined. Here, you know, this is just the decomposition. So the gamma is just the difference in error rate. So it's the error rate for light-skinned females versus dark-skinned females. And if you have a difference in that error rate in your data, you will actually see a high value, you know, statistically significant unfairness method. And that you can diagnose that you have an issue. Your model is not performing as well on your validation set for darker-skinned female faces in terms of predicting gender. You know, that said, does this framework, you know, give you a solution? Once you identify it, then you can go out and collect more data and see if that fixes the problem, or you can train multiple models and try and you know, institute whatever solution.
You're absolutely right, and that's actually really interesting. But I think more of data like I think this imprisonment example you gave is very interesting. When you have a bias that is kind of commonly distributed to all those people generating those data, then that's probably something that's going to be very hard to detect, or maybe you won't find this kind of issues in some kind of data set. So what I was just trying to say is that it's not that you cannot get a measure of how fair the whole process of generating the data, training the model, and then getting the results is in terms of the bias that we as people and ethic frameworks define bias, right? But that's the error example really
in the society. That's like, it's hard, right? Like if essentially it's just like it's like whatever algorithm that you train on that thing, it's hard to sort of fix that part.
Yeah, but it's a very interesting take to look at the data and see if there are bigger error rates in this group. Then you can see, okay, there's maybe an issue. I have to look into that. So that's probably important for more awareness for those kinds of.
At least for the problems where data generation is possible, you can actually fix that, right? In the case of Amazon's like face recognition, it is possible. You can actually take pictures and you can actually fix that, right? So
Okay, so following up, could you use the same metric to check the unfairness of the data set itself, or maybe compare different data sets from the same domain, let's say finance, and you have some data sets that are for some reason, maybe historical data, that are more unfair, and you can transfer some countermeasures from one data set to another?
Yeah, so I mean, it's important to remember this metric here, this line, this equation 1, this is an error rate of a model. So this y hat is a model prediction. This is a random variable, it's a very mathematical notation, but this is how much error and down here when we do the expected version, this is like the 0-1 loss accuracy score, or the false positive rate or the false negative rate of a classifier on a data set for a specific classifier. So if you have a benchmark model, you can compare that model on multiple data sets and generate multiple ones of these Ys, you know, and for per data set. Or if you have two models on the same data set, you can compare their unfairnesses.
His question was just, can you actually just give it
reverse?
Can you just call it unfair or not?
Right.
That's I think like unless you have like some sort of like predictions like already generated from that thing, like it's harder to sort of like, I mean, like how do you define then, right? Like, I mean, what is the task that you're trying to call it unfair? I mean, you cannot call, I guess, like you have to call like a task to be unfair, right? Like, I mean, college admissions are being unfair, or like face recognition is being unfair.
Yeah.
But the data set itself, you don't know how can you call it being unfair or unfair.
I think that's really very important part, because as I just said, if you have male and female as a feature, in some cases it can be absolutely valid that there's a difference, and in some cases you don't want to have this kind of differences.
But we can show you, like, if there is underrepresentation or something like that. You can do some analytics and say, like, if there is, like, okay, like what's like representation of like let's say you're doing you have all the university data, admissions data, and maybe you say that Ivy League universities have underrepresentation of like other races, right?
Yeah.
Those kind of things you can actually find from the analytics, but without a task, it's difficult to say like what's unfair or fair. I mean, that's just a construct of the society.
Actually, the idea that in this kind of groups, the error rate is bigger than in another group, that's very interesting. I mean, that's so easy, but it's absolutely obvious that there is probably an issue if this is the case, because when I think of people deciding things and you collect those decisions as data, then that's probably something where people would decide different based on if they are biased towards something or not. So that's really interesting take on this. Okay.
Sorry.
Yeah, go ahead.
I was just going to say a very interesting case study about the equalized odds criterion is actually with this recidivism case in prisons. Like, it's been known, you know, the previous mentality was you cannot train a model on gender because you might discriminate on gender. But what actually happens is in certain states, female offenders are much less likely on average to be repeat offenders in violent crime. And so it was actually, they were having a higher error rate for women when the models were not allowed to know if the person was a woman or not.
Yeah.
And it was predicting. And so states have actually gone back and changed their previous mentality, which was it's illegal to train a model on gender, and said, no, actually it's illegal to have your error rate be so much higher for women because you don't train a model.
Yeah.
And so I think these ideas, it's very important to keep this discussion going. There's a lot of papers coming out now discussing these different fairness metrics and the kind of pros, cons, and gotchas. You know, this paper points out a huge gotcha of like, if you make this metric 0, one of the ways you do it is, you know, if you have noise inherent in the relationship between your inputs and outputs, your model performance must provably go down to achieve parity, fairness and parity. And so this is pointing that out. But then, you know, this case of recidivism and gender, it's actually also points out that like if your concept is just as long as you don't use that input, you're fair. Well, actually, you can generate a lot of unfairness because of the model bias. That too linear of a model, and so it was overfitting. You know, it's not able to discern between these two groups. There's too much noise around men versus women. And when you add that extra feature, you actually cure some of the bias here by reducing the noise.
Yeah, very interesting. Also very, very important work. So that's something that I think in the rush of data science, people kind of forget to carefully evaluate their models and look what they're doing, especially when you are not predicting the next best ad, but something like in criminal justice or whatever that really affects people. Yes, so we are already on top of the hour. Does anyone have to say something very important? So go ahead, Krishna, maybe a last word from you.
Last word would be like, yeah, I mean, we'd love to engage with this community when we have like a private beta available, and we'd love to sort of get like people interested to dog food it and try it out and give us feedback. So
yeah,
I'm gonna
absolutely.
On the Slack channel when we have something ready, and I'd love to sort of have some people use it and give us feedback.
Yeah, absolutely. So if anyone wants to check out Fiddler, you will. So you're not published at the moment, right? So you are in kind of development mode.
Out. I can post some of the materials after the talk. Like I'll also post the slide deck for this talk, and also it's convenient. The paper is a little bit more terse read, so the slide deck and the poster are actually better. So for posterity.
Yes. Yeah, someone asked for the paper and the poster, but I think Andrew already posted them, so you will find them in the Zoom chat. I will also post them on Slack. And Krishna, if you have any updates on Fiddler, feel free to post them on the Slack channel. And yes, very interesting topic. So have a good evening, everyone, or good day.
Thanks for the opportunity. It was nice presenting this.
Yeah, thank you for presenting. Thank you.
Thanks for the presentation.
Bye. See you next time.
Yeah, thank you.